Hi everyone, today we'll continue with the second chapter, which is derivatives. So for this lesson, like I mentioned in the last lesson, we will be using differentiation rules to make our differentiation process more simple, right? We don't have to go through all the first principle, we don't have to use the definition for all the differentiation. If not, it will be very complicated, right? So I've actually made a video to derive all these general formulas, the derivatives for trigonometric function, exponential and logarithmic functions. So if you are interested, you can go ahead and watch those, or you can even try to prove it yourself. So for those who are new to calculus, means you didn't take advanced math or MF during your high school, these are the rules that are commonly used when we want to find derivatives. So just go through this very quickly. For this particular formula sheet, u and v are actually differentiable functions of f. So means if you have like a product rule here, it is the product of two functions, right? It's a product of two functions, then you use product rule. If it is u over v, means it is the quotient of two functions, then you use this formula. Now of course you have, as you can see here, what is this? This is actually composite function, isn't it? Composite function. So if you have composite function, they need to use chain rule. And in fact, it is not only for like 2 layers of composite function. It can be 3 layers, 4 layers, 5 layers, many layers. And this is very useful when it comes to, actually it is useful everywhere. But particularly for you, application question is the related rate question. It requires a lot of chain rule, okay? But for a polynomial function, the most important rule is the power rule, which is what we always said. Bring down power minus 1. Okay? Bring down power means you multiply the whole thing by the original power, then you go and minus the power. This is for polynomial functions. Then for trigonometric functions, and I think we have derived this in the last lesson, which is the derivatives of sin x is equal to cos x, alright? But you need to take note, what you need to take note is, for cos it is actually negative sin x. And for cotangent it is negative cosecant x. For cosecant it is negative cosecant x times cotangent x. How I usually remember that in the case where I don't have the formula sheet is that if you see the original function, look at the original function. If it starts from C, like cos, cotangent, cosecant, then the derivatives is negative. The others are all positive. This is how I remember. Okay, and if you get used to this, especially this and this, and also actually all of them, if you are very familiar with all of them, it will be very fast. You can do your integration very fast. Alright, you can spot what you need to do when it comes to trigonometric integral, what you need and what you need to do to get what you want. Okay, then the next one is exponential and logarithmic function. Like I said, I already proved it somewhere in the other videos. So if you're interested, you can go ahead and watch it. And if you just want to use the formula, yeah, you just use the formula, okay? But it is not always that simple. It's not just e to the power x or ln x. Usually you have something x, or it can even be e to the u. Usually it's like this. Then you need to use your chain rule, which you multiply by du dx. Similarly, if it is ln u, then you need to 1 over u times du dx. Okay, so you need to be very careful. This is the exponential and logarithmic function. And lastly is hyperbolic function. Hyperbolic functions is actually quite similar to what you have in trigonometric functions, just that the signs are different. Alright, so how I remember is for the first 3, which is sine, cos and tangent hyperbolic, they are all positive, whereas the rest, the 1 over, are all negative. Okay. Now, of course, after you do your differentiation, or before you do your differentiation, you need to simplify your function using whether identities or the properties of those functions, the natural law, something like that. Alright, so for trigonometric function, I just go through very quickly your definition. Okay, make sure you remember all of them. And this Pythagorean identity, double angle, and from double angle sometimes you need to derive out your own half angle and your compound angle. Okay, so this is for trigonometric limits. Trigonometric derivatives. What you need. Alright, then the next one is exponential and logarithmic functions. So I hope you know what is ln, which is natural log base e, or we read it as ln. Alright, so these are the algebraic properties. We have product rule, quotient rule, reciprocal rule, power rule, and I'm sure that you have practiced a lot in your high school or even in your college algebra, right? And also the exponential e to the x, exponential law. And there is something very important and very useful, which is this one, the inverse equation for e to the x and ln x. Why? Because as you can see, if you have e to the ln something, sometimes it's very complicated, right? You can directly say this is equals to that something. And wait, let me just prove it here. Let me just prove it here so that you can remember better. Okay, let me write the proof for you. I will just let this e to the ln x be y. Okay, so that I can manipulate both sides. Now I take natural log ln of both sides, ln e to the ln x. And now what? Now I can make use of the power rule here, bring down the power. Okay, so ln y equals to ln x times ln e. And what is ln e? Ln e means log base e of e. And if the argument and the base are the same, it is automatically equals to 1. Why? Because e to the 1 is equals to e. Okay, so the whole thing here will just be multiplied by 1. Hence, ln y equals to ln x and y equals to x. What is y? Y is e ln x equals to x. End of proof. Okay, so this is very useful. It's very, very useful. So similarly, if it is like ln of e to the x is equals to x, okay, then of course what happens if we have like other bases other than natural base e? So actually it's the exactly the same. Okay, like from just now we have like, what's that, e to the something, e to the ln ax is equals to ax, right? You just bring down the power, then you get ex ln a equals to ax, which is what we have here. Okay, then you also need to know the relationship between log and indices. If it is not base e, we call them indices. Okay, so a to the x if and only if log base a of. Okay, so this is the inverses of log, and these indices are the inverses of each other. Okay, then this one is very similar to what we had just now. And the indices and logarithmic rules, this is your product rule. Okay, two of them are your product rule. Then you have your quotient rule. Then you have your power rule. They're actually all the same. These rules are actually derived from your algebraic properties of natural logarithm. Okay, then if you want to change your base, this is change of base. Because sometimes if you have a lot of different base, very hard for you to simplify, right? So usually in mathematics and calculus, a very common base that we will use is log base e, which is ln. So if you want to change log base a of b to ln, just that ln b over ln a. The argument is on top, the base at the bottom. This in calculus, in math, alright? So in sciences, the base that they always use is actually log base 10, or write it as lg, okay? lgb over lg8. Why? Because in scientific, you see a lot of scientific notation like times 10 to the power 9, times 10 to the power -4, etc, etc, right? So it will be easier if they use base 10. Alright? Then the next one is hyperbolic functions. You need to know the definition. Okay, you need to know the definition, and you need to know the identities. The identities are actually quite similar to the one in trigonometric functions, so make sure you don't confuse yourself. Alright? I will directly jump into the exercise, and we'll explain the rules, the formulas along the way. Okay, we need to use differentiation rules to find the derivatives. Let's look at the first one. Okay, so the first thing that you see is maybe, oh, I see a product of two functions. Can I use product rule? Yes. But for this particular question, actually you can also expand, because it is not too bad to expand, right? You just use your FOIL operation, right? So you actually have two methods to do this, which is the first one, method 1, you expand, or method 2, you use product rule. I will show you both methods. Alright, so if you want to expand, like I said, you use FOIL operation. Just make sure you don't expand wrongly. 10x squared minus x squared, sorry, this one is cubed. You see, I already made my mistake here. Plus 15x squared minus 12x. Alright, so 10x cubed, 15 minus 8 is 7. Then now you can differentiate. Differentiate, like I said, bring down the power minus 1. 3 times 10 is 30. Bring down the power minus 1 is 14. 2 minus 1 is 1. Minus 12. X minus 1 is 1 minus 0. 1 minus 1 is 0. X power 0 is equal to 1. So this answer. Okay. Just bring down the power minus 1. This is your power rule. Then what if I want to do product rule? Can you do product rule? Yes, huh? Okay, method 2. If I use product rule. Okay, let me copy the function here. 2x plus 3, 5x squared minus 4x. So if you want to do product rule, you need to know who's your u, who's your v, right? Who's your u, who's your v. And for product rule, it actually doesn't matter, because u times v is the same as v times u, isn't it? But for quotient rule, is different. U over v is different from v over u, okay? So for product rule, just simply 2x plus 3, so du dx will be bring down power minus 1. Okay, 5x squared minus 4x, so dv dx is 10x minus 4. Okay, then your f prime x will be, go back to the formula, u dv dx, v du dx. Okay, u dv dx, then plus v du dx. Okay, then you just go ahead and simplify this. 20x squared minus 8x plus 30x minus 12 plus 10x squared minus 8x. So 20 plus 10 is 30. Then 30 minus 16 is 14 minus 12. Finish. Okay, so this is what happens if you want to use product rule. Actually, both of them are quite simple, right? You don't have to do a lot of complicated stuff. Okay, then question number 2. Obviously, you see a quotient of two functions. So again, you need to know who's your u, who's your v. But before that, can we do the expand? No. In this case, it's not expand and you simplify, right? You can, right? Because you only have one term at the bottom. So method 1, you go and simplify before you do anything. Before you differentiate. Okay, or you can use quotient rule. So if you want to simplify, I would recommend you to write it like this first. Okay, then you just play with your indices. X to the 1 times x to the negative half. 1 minus half is half. And the reason I want to write it in indices form so that later it's easier for me to bring down the power minus 1. Okay, then plus 1 over 2 x to the negative half. F prime x will be bring down the power minus 1, bring down the power minus 1. Simplify. Okay, and if you like, you can write it like this: 5 over 4 sec x minus 1 over 4 square root of x cubed. Okay, so what happens if I want to use quotient rule? Like I said, you need to be very, very certain about your u and v. Okay, so method 2, using quotient rule. Let me copy the function fx. Right? So the one on top, we call them u. The one at the bottom, we call them, v equals to 2 square root x. And it is actually 2x to the half. Okay? Then you just differentiate. du dx is 5. dv dx is, you bring down the power minus 1. And simplify this is x to the negative half. Okay? Then now we just plug in your formula. It's a little bit complex for a quotient. It is v du dx minus u dv dx. That's why I told you it's very important for a quotient because it is minus. For plus, it doesn't matter, but for minus, it matters. Okay? V du dx minus u dv dx. V du dx minus u dv dx over v squared. Okay, then you just simplify. Half minus 1 minus half is half. Okay, then 2 squared is 4x half and 2 cancel. Then you just simplify, just open your bracket. 10 minus 5 is 5x to the half minus x to the negative half over 4x. There you go ahead and simplify your indices. 5 over 4 x half minus 1 is negative half minus 1 over 4. Negative half minus 1 is negative 3 over 2, which is the same as just now, right? Very nice. Okay, then moving on to the third question. Alright, now we have trigonometry. And obviously you saw a product here, then you have a sum rule here. And just now also got sum rule, right? Just now also got. Anyway, for the first part, you can actually directly do dy. It's not very complicated. So if you can see it, if you will do a lot of exercises, you should be able to do it directly. Okay? Follow me closely, yeah? U dv d theta. What is the derivatives for sine? Cos, right? Cos theta. Plus v du d theta. You differentiate theta, you get a 1. So it's just sine theta. But don't forget your cos theta at the back. Cos theta, the derivatives is negative sine theta. And this sine theta and sine theta can cancel. At the end of the day, it is just theta times cos theta, finish. Okay? moving on to the next one. Okay, so this time you need to use chain rule, right? Because you have actually a composite function. Am I right? And of course, you can go ahead and expand this if you know how to expand to the third power. But now I just want to show you chain rule. Chain rule, like I said, is for a composite function. So you need to split it into several simpler functions. Then you differentiate. Then at the end, you combine everything together. Alright? So this is the direction. For now, I will just let this piece be my u. So y equals to 2u cubed. U will be at x minus 1. And now it's very simple. dy du. You see? Make sure you know that who is your parameters. Now it is dy du. Bring down the power minus 1. du dx will be 8. And now dy dx equals to dy du times du dx. If you are not sure who multiply by who, in the case that you have a lot of them, like especially in your related rate question, always check. You see this du and du can cancel. So if you combine, you'll get back your dy dx. You must always get back what you want. And in this case, it is dy dx. Okay? Just multiply. dy du was 6u squared times 8. So it is 48u squared. But this is not enough. Who is your u? You need to tell me in terms of x. So your final answer should be 48x minus 8x minus 1 squared. This is your final answer. Okay. And actually from chain rule, we also derive a general power rule. Okay. So I will use the same example here. For general power rule, you just same thing, bring down the power. 2 times 3 is 6. 3 minus 1 is 2. Then you copy the inside function. Then now you differentiate the inside function, which is actually the same, isn't it? Okay, so this is a general power rule. You bring down the power, copy the inside function, power minus 1, differentiate inside. Okay, number 5. As you can see, we have a few layers of chain rule that we need to solve, right? Okay, so we do it slowly. First layer, 4 sine u. Second layer, square root of 1 plus square root of t. But this is still very complicated, so maybe like this. Square root of v. Then v equals to 1 plus square root of t. Is that good? Okay, yeah? So now, you go and differentiate. dy du is 4 differentiate sign, you get a cos u. du dv is, this is actually v to the power half. Then you bring down the power minus 1, and this 1 over 2 square root v. Okay, so if you have done a lot of like exercises, you should be able to know that it is just like that. Okay, then dv dt, like I said, you differentiate a constant, you get a 0. Then this is just like that. Okay. Then now it's time to combine all of them. dy dx, dy du, sorry, it should be dy dt, dt times du dv times dv. Like I said, always check du cancel, dv cancel. Okay, nice. For cos, who's your u? Your u was square root of, who's your v? 1 plus square root of t times 1 over 2, who's your v? 1 plus square root of t times 1 over 2 square root of t. And the most you can do is you simplify this together. And that's it. cos 1 plus square root of t over 1 plus t times square root of t. Yeah, this is it. Okay, it's a little bit messy here because there are a few layers going on here. Okay, moving on to the sixth question. So it's trigger again. It's chain rule again. dy dx will be differentiate outside function. Differentiate a cos, you get a negative sign. Then I think you better put a negative. Put a bracket here because you have a few layers. Differentiate outside, copy inside functions. Copy inside function. What happened now? Okay. Copy inside function. Then times you differentiate inside function. You differentiate 5 sine, you get 5 cos. And you have another layer, right? What happened now? You copy inside function times you differentiate inside function. And I think the most you can do is to take out the constant, negative 5 over 3 sine 5 sine t over 3 times 5 cos t over 3. This is the most you can do. Okay? So you just need to do a lot of exercises, then you get used to this chain rule. You should be able to do it very quickly. Okay, next one. Oh, again is chain rule. And this time the chain rule is more complicated. Okay? So whenever you see a tangent square or sine cube or whatever, you know that it means tangent, whatever inside, the whole thing squared, right? The whole thing squared means what? Means you can bring down the power minus 1, then you go and differentiate whatever inside. Okay? So if you want to do chain rule, if this one you want to do chain rule, it involves at least 1, 2, 3, at least 4 layers. So no need, you just directly do. But I will just tell you what I'm doing here. Okay, so tangent u squared, bring down the power minus 1. So now it's just tangent of u. They need to multiply with the derivatives of du dx. And who's your u? Your u is sine x cube, right? Actually, I skipped 2 layers. All right, du dx will just be 3 sine x square, differentiate sine, you get a cos x. So it is 3 sine square x cos x. Then you just go ahead and multiply all of them together. Okay, so dy dx will be 2 tangent, who's your u? U is sine cube x times 3 sine square x cos x. And I think this is the best you can do. Or you can combine 3 and that one together. Okay, sine square x cos x. Yeah, this is the best that you can do. Okay, moving on. Oh, we have our ln here. So actually for this particular question, you have 2 choices. You can either use chain rule or you can use the log properties. And I will show you both ways. If you want to use chain rule, okay, you just write y equals to ln u, and your u is 10 over x. 10 over x means 10x negative 1. So du dx will be bring down the power minus 1. And what is the derivatives of our natural log? Ln. If you're not sure, go back to the formula. It is just a very nice 1 over x. Okay, 1 dy du, it is 1 over u. This is dy du. If I write this is dy dx, then this has to be dy du times du dx. Okay, so it is 1 over u times negative 10x negative 2. And who's my u? U is 10 over x. This 10 and 10 can cancel, and you play with that one. It is actually negative x times x with negative 2, which is negative 1 over x. Okay, so this chain rule. And actually, no need to do this kind of all kind of chain rule here. Like, if you are very expert already, you can actually just array y equals to dy dx equals to 1 over whatever inside. Then you go and differentiate the inside function, which is 10, then negative 10 over x squared. Okay, then this 10 and 10 can cancel, 2 can cancel, negative 1 over x. Okay, you can do it in like just one step. Okay, then what about if you want to use the log properties? I'm sure some of you have seen it, right? Okay, if I want to use log properties, means I need to simplify this before I differentiate. Okay, so what is this? This is actually, you can use your quotient rule of logarithms, right? Quotient rule, this one. Hey, wait, what's it? This one. Okay, so now y equals to ln 10 over x equals to ln 10 minus ln x. And very happily, ln 10 just happens to be a constant. So you don't care, you differentiate a constant, you get 0. Okay, dy dx equals to negative 1 over x, finish. Okay, even if it is not a constant, you just go ahead and differentiate. It doesn't matter. Okay, number 9 is ln, and inside we have secant and tangent. So it's the same, like I said, if whenever you have ln, then inside this 1 over whatever inside, you go and differentiate whatever inside. Okay, you differentiate secant, it should be a positive secant x tangent x. Okay, differentiate, you get a secant theta tangent theta. You differentiate tangent, it should be a positive secant square theta. Okay, secant square theta. And what can you do here? You can actually factor out your secant, right? Secant theta. Oh, and you can simplify with your denominator. So at the end, it is just a secant theta, finish. Okay, so you need to be very familiar with the chain rule and also how you manipulate the ln derivatives. Okay, just that if you have like y equals to ln of ln x again, you know that you can straight away do, you cop 1 over whatever inside, you differentiate inside, you get 1 over x, and that's it. If it is another layer, got another layer 1 ln x, that is, don't panic, 1 over whatever inside, differentiate this layer. Okay, it is 1 over whatever inside times, differentiate this one, it is 1 over x. So this is it. Okay, so do a lot of exercises, get used to this. You should be able to do it very quickly. Okay, number 10. Okay, it's a product rule and also exponential. Am I right? So we'll do product rule. Dy dx will be copy the first function, differentiate the second function. Okay, what is the derivatives for e to the x? Still e to the x, right? But now it's actually a little bit of chain rule here. You play with e to the u, then you differentiate, you get e to the u, and now your u is negative 2x. du dx is negative 2. So you need to multiply them together. Okay? So it is just e to the negative 2x times negative 2. Plus, remember you are doing a product rule, yeah? E to the negative 2x, copy a second function, multiply with the derivatives of the first function, which is the 2. Then you just go ahead and simplify. I think you can factor out 2e negative 2x, right? Then I'm going to write this one first. You factor out, you can just have a 1. Then minus 1 plus 2x. 1 minus 1 is 0. 4 negative 4x e negative 2x. Okay? Number 11, okay, we have log with different base. So actually for this kind of question, you have two options again. You can either you change to log base e, which is natural log, or you can just directly use what you have here, this one, 1 over x log a. But you know, as you can see, it is actually more complicated, and actually it is derived from the chain rule. Okay, so 1 over x log a. Then you know that you need to use product rule anyway, product rule. But if we change it to log, maybe we don't have to use product rule, right? Because I think this log base 3 and log base 9, if you combine two of them together, something will happen. So let me just try the method 1 for you. First, of course, I will show you both ways, alright? Before you differentiate, you change your base, and remember your change of base formula, ln r, ln 9. And what is this ln 9? 9 is actually 3 squared, right? And you know what? This is just ln 3 times 2 ln 3, which is 2 times ln square 3. By the way, this one, I think I better write it for you. Ln square 3 is the same as ln 3 square. But if you have ln 3 square like this, means it is 2 ln 3. Okay? Be very careful about this. So this will just be the one on top, ln square r. Okay, ln square r. And now you just have to differentiate, and you don't actually have to use quotient rule here. Why? Because the entire thing here, 2 ln square 3 is a constant. Okay, so you don't care. Just directly do your dy dr will be 1 over whatever you have at the bottom. This is a constant, am I right? This is a constant. Then you differentiate this ln square r. Bring down the power minus 1, differentiate inside function. One more time. This is same as ln r square. Bring down the power, differentiate inside, and combine all of them together. Okay, combine with the constant in front also. So 2 and 2 cancel. Nothing else you can do. Okay, so it is just ln r over r ln square 3. Okay, finish. So what happens if you want to use this way? I think it will be very complicated towards the end. At first it is very easy, you just do the product rule and just directly substitute in. But when you want to simplify, it will be very, very complicated, I think. Okay. So let's say you want to do it that way. Y equals to log base 3r times log base 9r. Okay. So dy dr will just be, okay, I think I better write here, d dx of log base a of x is 1 over x ln a. Alright? Product rule. Copy the first function, differentiate the second function, x ln a. Product rule. Copy second function, differentiate first function, x ln a. Then, see, I told you it is very complicated when you want to simplify. You need to change your base anyway. Over r ln 3. See, you have all different bases. And obviously you know that this shouldn't be your final answer. You need to simplify. And I think you should be able to get the same answer as this one. Okay, I'm not going to do it here. So yeah, for this particular question, I recommend you to change to ln first before you differentiate, so that it is easier for you to simplify. Okay, that's just it. Number 12. Okay, we have indices, and you know that it is a product rule plus quotient rule on top. So just do it slowly. Okay, this is your v. Du d theta will be a product rule, right? Copy first function, then okay, copy first function is theta. You differentiate 5 theta is 5 theta ln 5. Okay, forgot to show you the formula. If you differentiate anything other than base e, you need to multiply with a ln a at the back. Okay, which is actually your chain rule. Ln 5, then plus copy second function, differentiate theta, you get a 1. Minus copy the function on top, differentiate, it's a negative. 2 you don't care, then you know that it is x ln a. Okay, then just square this. And I don't think you should expand it, you should just leave it like this, at the one at the bottom. And now, time to factorize. I think for this part here, you can factor out your 5 theta. 2 minus 5 theta. Theta ln 5 plus 1. Minus becomes a plus. Theta and theta can cancel each other. 5 theta over ln 5. There's not much you can do, you know. The most you can do is you multiply top and bottom by ln 5 to get rid of this fraction here. Okay, 5 theta, 5 to the theta power, ln 5. I'm running out of space here. Plus 5 theta, 2 log. Okay, miss out something. Should we have a minus here, right? Minus. This is what happens if your handwriting is too ugly. And this is it. This is the best that you can do. Okay? Number 13. Oh, finally we have hyperbolic. But for this one is super easy, huh? Dy dx is constant multiple, don't care. Differentiate sign, you get a cosh. copy inside function, differentiate inside function. So simplify, finish. Okay. Number 14. Oh, we need to use chain rule again, right? And okay, chain rule, then yeah, chain rule. Both of them are chain rule. Okay, dy dx is ln. Like I said, whenever you see ln, 1 over whatever inside, differentiate inside, differentiate sign, you get a cosh. Okay, minus constant multiple, power bring down, power minus 1 times differentiate inside, differentiate cotangent hyperbolic. You see, start with C, right? So it should be a negative. Negative what? Not sure. Not sure. Refer to formula. Cotangent, it is negative cosecant hyperbolic square. Okay, negative cosecant hyperbolic square x. Then we just go ahead and simplify this. Cos over sine is cotangent hyperbolic. This will just be negative, negative become plus. Half times 2 is 1. Cotangent hx cosecant h square x. Okay. Factor out cotangent hyperbolic. Why? How come I got so many h? Okay. I hate it when you are doing hyperbolic and the variable is h. It's so damn confusing. Then 1 plus cosecant hyperbolic square. And this one is very familiar, right? This is actually one of your identities. 1 plus cosecant hyperbolic. 1 plus cosecant hyperbolic is cotangent hyperbolic square. Okay, so it is cotangent hyperbolic times cotangent hyperbolic square. So combine together, cotangent hyperbolic cube x, finish. Okay, that's why I said that the definition and the identities, the properties, the laws, the rules are very important for you to simplify your answer. Okay? Then the last question for today. Oh, there's something that I want to talk about this question. Of course, you can directly do product rule and your chain rule, but whenever you see you got hyperbolic function and whatever inside your hyperbolic function is a ln something, then I would recommend you to convert it back to the definition, which is in terms of e to the something. Okay, this definition for secant hyperbolic was this one, right? 2 over e to the x plus e to the negative x. Okay, so why I want to do this, we just see. Okay, I don't touch this one. 2 over e to the ln x. Secant is 1 over cos. Cos is plus. Okay, e to the negative ln x. The reason I want to do this is because, remember from earlier, e to the ln x is what? E to the ln x is just x. That is why I told you that it is very useful, right? So I will just write this as 2 over x. And what is this? E to the negative ln x. It's actually e to the ln x negative 1, which is e to the ln 1 over x, which is 1 over x, plus 1 over x. But it's not nice, right? So I multiply both top and bottom by x squared plus 1, 2x over x squared plus 1. You see? You can simplify. And y will just be 2x, and your dy dx is just 2. Finish. Okay, so you see, if you convert it back to ln, which is convert it back to definition, it will be so much easier. If not, you have to do what is the derivative for secant hyperbolic, or is negative, what's that? negative secant hyperbolic, tangent hyperbolic, then you need to simplify, you need to do a lot of work. But if you convert it back to definition, it is so much easier. Provided that whenever you have insight, it's like ln something. Alright? So that's all for today for the differentiation rules. In the next lesson, we'll talk about the derivatives for the inverse function. Then we'll combine everything together. Alright, so for this particular topic, actually you just need to do a lot of exercises, get used to the formulas, get used to all the chain rule, product rule, quotient rule, and you should be able to do it very quickly. You should be able to spot which rules to use very quickly. Alright, so that's all for today. See you guys in the next class.